2, 1. Okay, there we go. So the reading for today is going to be from today we're going to go over chapter 9. Actually, we'll do a little bit of cleanup from chapter 8 and then get to chapter 9. And then I hope, I think we can sort of do a reasonable job in doing as much of chapter 9 as we need. And then we'll get to chapter 10, which is about group theory, which is sort of, that's the last abstract object that we haven't, the last of the major abstract objects in abstract algebra that we haven't introduced. I mean, we've sort of made references to it, but we haven't really introduced it. And so we'll talk about that on Monday. So we do have a problem session on Friday from 10:30 to noon. So remember, so this is going to be and at that problem session, you're welcome to talk about problem set 10. Oh, why is it still at 14? Problem set 10 or whatever else you want to catch up on. Right, so remember, so we have these deadlines, but they are, so remember, there's two things to remember. One is that we have these deadlines, but they are completely all flexible. That's worth typing out again. Remember, so let me, remember two things here. Remember, why is it still 14? So remember two things. One, all deadlines are flexible. That's true. And we have until the end of the semester to get everything done. But two, also remember that homework is 35% of your semester grade. And much of that, maybe even most of that, will be just getting it done. As much as you can get. So, and I think that this is, I've been told, and I think this is true, that a sort of fairer way to do things, a more fair way to do things during quarantine is to put more emphasis on what you might call asynchronous assignments and things that you can do in your own time, because time is weird now. Days have no meaning. It's like we're living Groundhog Day over and over again. But so that's why homework is now 35% of your semester grade. But if you can get it done, then that would be a big plus for you. But on the other hand, you do have to get it done. It's not so easy. So so please keep those two things in mind. So are there any questions about where we stand in the course before we get started for the day? Everybody good? Is everybody ready to rock? Thank you, Jennifer, for picking a song for my misspent youth. Though I didn't misspend it, like, as I always say, I didn't misspend it by like stealing hubcaps or whatever. I actually just like misspent it. I like spent a lot of time playing D&D and watching Doctor Who, which is like and Monty Python and all those classic nerd things. Those are simpler times. So everybody ready to move on? Say yes. Yes. Yeah, y'all are out there saying, yes, let's move on. Please don't do any more old man things. Okay, fine. So let's pick up where we left off. Where were we? Oh, yes, we were at the BCH theorem. So let C be a cyclic code of length n over F2, and let C be generated by a polynomial g of x for some, and remember, when you have a cyclic code of length n, it's going to be generated by some polynomial dividing x to the n minus 1. And so, well, it's the same as x to the n plus 1, but okay, x to the n minus 1. Then suppose E is an extension FQ. So E is so this is sort of like between notations here, where Q is equal to 2 to the E, to the little e. So E is a field of order 2 to the E, such that for some delta, for some positive integer delta, and some alpha in E with the order of alpha exactly equal to n, we have that this mysterious polynomial G happens, the generated polynomial G happens to have roots alpha through alpha to the delta minus 1. So if we can achieve that miraculous state, so this is the whole thing that we're working up to in chapter 8. If we can somehow achieve that miraculous state, then we have a code of what's called a BCH code. So and if So if C actually is not a BCH code, it's maybe this particular BCH code, which was sort of built using delta, and we call delta the design distance of the code C. And it might, I think as you'll see in the homework, there is sometimes you'll get actually a better code than you were hoping for. Sometimes you just sort of magically pick up some extra distance, but just because of the vagaries of what we're about to do. But yeah, you're guaranteed at least a design minimum distance of delta. In other words, to get a BCH code of designed distance delta, we want the smallest possible degree polynomial g of x that's divisible by x minus alpha squared, all the way up to x minus alpha to the delta minus 1. Or in other words, what we want is the least common multiple of the minimal polynomials. I say that 10 times fast. Minimal polynomials. We want the least common multiple of the minimal polynomials of alpha through alpha to the delta minus 1. And so here's the algorithm. So so this is all well and good, but I think in practice, what I'm going to have you guys do on the homework is actually go through this recipe for creating a BCH code. So if you want to sort of find a good code of, I don't know, length 1023, that's actually plausible, as we'll see. Then here's what you do. If you took e equals 10. Then that has a pretty good chance, and you sort of go through this, you have a pretty good chance of getting a good code of length 1023. So choose a finite field E of order 2 to the little e. And what we're going to do is we're going to choose an alpha in that E and let n be the order of alpha. And note that often what we're going to do is we're going to choose alpha to be a primitive root of E. So we know that there is some order. Remember, we know that I guess I should make this 2 to the e minus 1. So this is really 2 to the e minus 1. So remember there always is a primitive root of any finite field, and so there will be some element of order 2 to the e minus 1. In that case, the code we're going to make, which is sort of up to nature to make it a good code, but we'll, to determine how good that code is going to be, but our code will have length n. So then the only part that we really choose, the only part that's not dictated by nature, is we choose our design distance delta. And so remember, and this will allow us to correct. And why do we care so much about the design distance delta? The reason we care about the design distance delta is that we are going to correct at least a floor of delta minus 1 over 2 errors. Right. So that's why we want, so generally we'll choose delta to be relatively large, or at least sort of large enough until G becomes like too big, and until G becomes too big and sort of you don't, and then your information transmission rate becomes very inefficient. So if we let G be the least common multiple of those minimal polynomials m1 through m sub delta minus 1, then C is the cyclic code of length n generated by that G of x. So if we choose our Q and our alpha wisely, or in other words, if we get lucky, I mean, so or nature agrees with our choice, basically, then we get a code with a large dimension, so a high rate of information transferal, and a high rate of information transfer, and a large minimal distance, and also a lot of error correction. So that so again, we don't. So the odd thing about this BCH scheme is that we don't really choose the length of a BCH code. And so now if you go and look at in Wikipedia has a nice entry on BCH codes. I mean, it's mildly complicated, but you are now in a position to understand it. You guys are now experts in this. Maybe even compared to, and certainly compared to like regular folks, and maybe even compared to some engineers who do this for a living. But okay, now you guys are now experts in this kind of thing. You look and you'll see that all of a sudden, like, hey, well, look, okay, maybe not engineers who do this for a living, but then most you now know more about this than a lot of engineers who at least work in the field adjacent to this. Anyway, so if you look in the Wikipedia entry for BCH codes, the length of those codes are going to be like 31, 63, 127, 255. They're all powers of 2 minus 1. And the reason is because you don't really get to choose, like we human beings don't get to choose how long our BCH code is going to be. In order to make a good BCH code, you generally want to have a code that's length 2 to the something minus 1. That's often what happens. So so I don't know if hi, question. Yeah, M127 with a BCH code of length 127. Sure. Yeah, I'm sure there's something good up there with. Oh yeah. Well, yeah. So you won't want to go out to M127. Well, I'll sort of do an example in a minute. I guess probably. Yeah, I mean, sort of what you want to basically what you want to do is you want to kind of go out to the extent until the degree of G is about half the length of the code. That's usually that's often where you sort of end up getting an optimal result. And though actually, I should say, since somebody brought up since Johnny brought up the specter of actual examples, in practice, actually, what happens is that as the codes get longer and longer, the BCH codes get worse and worse. And actually, and I don't know of any. And actually, here's an open problem. Actually, I personally don't know. It's a very interesting thing. So a guy named Shannon, about 80 years ago, proved that there exists really good codes. Like as the length of n gets very large, as the length of your code gets very large, there exists codes that have high information transfer rate and also error correcting, good error correcting properties. So through using some very abstract thing, Shannon proved that codes exist. But as far as I know, I think maybe there's a candidate recently, but as far as I know, there's not really a sort of well, I mean, this is still an open problem in coding theory. That's why coding theory still exists. There's an open problem of finding code that has good high dimension, therefore good information transfer properties, has a large minimal distance, therefore good error correcting properties, and also has and actually there are code. I think there is not. Recently, there's been a scheme to sort of achieve both those things at the same time. But then what happens is the decoding is very difficult. So if you can find a sort of lasting scheme of a way of making codes that has large dimension, high information, so large large minimal distance, and therefore good error correcting, and also has a reasonable decoding algorithm, something we haven't gotten into at all about the BCH codes. There is one, but we haven't discussed it, which we won't discuss. Then you can make, a lot of money. Like that's like a career if you can do that. You could spend your whole life making money off those codes. So anyway, yeah, we've gotten, the title of the course is industrial applied industrial mathematics or algebra, and this is real applied industrial algebra, and that you can go out and make money with this stuff. Anyway, that being said, I think are there any questions before I do an example? I think the example is the thing that really is going to illuminate what's going on. So any quick questions before we do an example? I can say Bose and Chaudhuri, and if you look this up in Wikipedia, there's a Dutch, H is some Dutch fella whose name I have never absorbed. Anybody about there of Dutch descent? Let me so challenge. I'll put a challenge in. Some of you email. I know somebody will. Maybe you can do this now if you want, but I think actually this next bit you'll want to pay close attention to because it's on your homework. But I challenge find a YouTube clip of someone pronouncing the inventors of BCH. Which you say just put in the chat, like the three they didn't work together. I think they all sort of figured this out at the same time. I think in the 50s and 60s, something like that. So Bose, Chaudhuri, and then I'm just going to copy and paste this from the chat. Thank you, Ryusei, for pointing that out. So let me see if I can. So the folks who invented this coding, I won't do this, are Bose, Choduri, and the third guy. And if anybody can, a special no prize, here's a challenge in your copious free time. Go find a YouTube video where somebody pronounces this last name correctly. I believe it's a Dutch person. Okay. Anyway, so let me do something. Let me do something similar to your homework. That's maybe more productive. Okay. So right. So remember, let's actually create a code. Let's describe how to create a code of minimum of length, as we'll see, 31, and minimum distance at least 7. Right. So alpha is, so let E be the code of let E be the field of order 32, and suppose we know a primitive element alpha of E, and so the order of alpha is 31. And I want to use this element alpha of order 31 to construct a code of length 31. So n will be equal to 31. I want to construct a code of length 31 that has minimum distance at least 7. And so now I have to start computing orbits. So the orbits are, well, remember, the idea is you start off with alpha to the 1 and you start squaring it, alpha squared. But after a while, I get bored with that. So I'm going to use this bracket notation. I'm going to say that's 1, 2, 4, 8, 16, and then 32. But remember, alpha to the 31 is equal to 1, and so exponents are all taken mod 31. So exponents all mod 31. And so 16 times 2, remember, the squaring corresponds to multiplying the exponent by 2. We get an exponent of 32. And so 32 is, and 32 is 1. And so that's one orbit. That's one Frobenius orbit, right? And this is an abbreviation for alpha to the 1, alpha squared, alpha to the 4th, alpha to the 8th, alpha to the 16th. Okay, so, and now we've gotten 1, 2, and 4, and we have 3, and we need up to 6, right? So the BCH theorem says that we want to have all the orbits that include all the powers of alpha from 1 through 6. So 1 through 6, right? And all we want G to have roots alpha to the 1 through alpha to the 6th. So the next orbit is going to be 3 and 6, and then 12, and then 24. Twice 24 is 48, but mod 31 is 17. And 17 times 2 is 34. Mod 31 is 3, and so that closes up. And so remember, these green arrows represent sort of doubling and going back to the beginning, mod 31. And so now we get, and now we've gotten 1, 2, 3, 4, 5, 6. And so now I guess, so the only orbit left to compute is the orbit of 5, 10, 20, 40, 40 mod 31 is 9, 18, and then 36 mod 31 is 5, and so we go back to the beginning. So this is 36 mod 31, and over here we're using the fact computing 34 mod 31. And the 31, remember, because remember that 30 is 31 and not 32. This is always, these plus or minus ones are the most confusing part of this. This is 32 mod 31, and the fact that we're taking exponents mod 31 comes from the fact, if your field has if your field has 32 elements in it, then your exponents, if your field is order 32, then the exponents you compute are going to be mod 31, and so well, that's just very confusing, but you just have to remember that. And then so now we've gotten our final our final orbit. And so now we've gotten everything up to 6, and so we're done. And so what we're going to do is we're going to take so let me pause here. So are there any questions now about why it is sort of what is it that we just did? I mean, I guess can you at least duplicate what we just did, and does it make sense as to why we stopped? So so is that good, or are there questions? Why do we, okay? So Johnny asked, why do we stop? Right. So here's why we stopped. Let me sort of start to try to say again why we stopped. We, in the end, what we want, the least common multiple of the minimal polynomials M1 and M2 all the way up to M6. M sub I comes from the orbit of I. So M sub I comes from the orbit of I. And so let me point out in one more different color as to sort of why. What colors have we not used yet? Oh, actually, I want pen. I don't know. Let's try this peach. So this is the orbit of both 1, 2, and 4. And as we'll see, actually, let me write out one of the minimal polynomials. That might help. So so that orbit 1, 2, 4, 8, 16. That tells us, because we start off with 1, that gives us the minimal polynomial of alpha to the 1, which is going to be x minus alpha times x minus alpha squared times x minus alpha to the 4th times x minus alpha to the 8th times x minus alpha to the 16th. And somehow, by some miracle, so let me, I mean, I'm not going to make you do this. Maybe I made you do this once, but let me point out that by some miracle, it's all, if I multiply this out, if I sit here and I multiply all these things out and I sort of use whatever rule it is that I used to define F32, then by some miracle, all this stuff somehow cancels. And then we get that all coefficients are either 0 or 1. I think I did one example. I did one example this last time for degree 3, which is sort of about, about as far as I'm willing to go in terms of my patience, I guess. Yeah. So, so the point is that this is now somehow because of abstract stuff, the abstract stuff that we discussed about orbits and sort of this being invariant under symmetry, then it must be the case that when I multiply this out, I'm going to get a polynomial with coefficients in F2. So there's all the alphas sort of go away, and this somehow becomes a polynomial just with coefficients in 0s and 1s. Anyway, so this is the smallest such polynomial with coefficients just 0s and 1s that when you plug alpha into it, you get 0. But because this also has 2 as a root, this is now the minimal polynomial of 2 of alpha squared, and also is the minimal polynomial of alpha to the 4th. And so so what we want is the minimal polynomials 1 through 6, and this sort of knocks out 1, 2, and 4, and then M3, which is x minus alpha cubed, all the way up to how's that orbit? That orbit ends up with x minus alpha to the 17. That's the minimal polynomial of alpha cubed, and also the minimal polynomial of alpha to the 6th. And then we have the minimal polynomial of alpha to the 5, x minus alpha to the 5, and that orbit goes up to 18, x minus alpha to the 18. And so, right. So, in the larger sense, so Johnny, let me finally get back to answering your question. In the small sense, in sort of the immediate sense, well, why do we stop? It's because we stopped because we needed to go. We wanted delta equals 7, and we wanted to go up to 6, which meant we wanted minimum distance 7, which means that we need to go up to 6, which is 7 minus 1, which means that we stop as soon as we get all the orbits that include all the numbers. As soon as we get enough orbits that include all the numbers 1 through 6, then we stop. So sort of in terms of like, what are you doing your homework? We stop because we stop because all the numbers 1 through 6 are included in some orbit. So there after like 10 minutes. Sorry, Johnny. I can finally give a short answer to your question. We sort of in terms of like, what do I need to know? What do you need to know to do the homework? We stop because we've done enough orbits to include all the numbers 1 through 6, and the reason that we only want the numbers, we only need to have all the orbits that include 1 through 6, is that we just need the minimal polynomials of m1 through m6, and they're all included. Oops, except I did that last one wrong. So Johnny, I think I maybe over answered your question, or but was that at least helpful to some extent?
Yeah.
Okay, thanks. Okay, good question. All right, so there we go. So that's our generator. Oh yeah, and so I guess, well, do I want to say this now or? Oh yeah, and so so now we see. So then let me sort of add some more details about this code. This is if you look, this is good. Oh geez, did I mess this? I think I messed this up. This is not. This is the 3116. Oops. Let me pull back out here. Oh, my thumb looks so large there. So let me go back out here. This is actually the 3116, as we'll see. 7 BCH code. And like I said, when the dimension turns out to be sort of roughly half of the length, that's when you sort of know that this is as good as it's going to get. Just as a rule of thumb, or maybe it's just my. So some details include. So g of x is going to be equal to, it's the product of m1 of x, m3 of x, m5 of x. So it's just those 3 polynomials, because m2 and m4 and m6 are, you kind of get those for free because they were already included in the orbits. So the degree of g is 15, because each of these terms has, each of these orbits has 5 elements in it, which means that there's 5 linear terms, that each of these minimal polynomials is a product of 5 linear terms, which means that each of them has degree 5, and so degree 5 times 5 degree 5 times degree 5 times degree 5 gives you degree 15. And so remember, the dimension of your code is going to be equal to, I should have just left these numbers blank and fill them in as I went. But anyway, the dimension of your code is the length of your code minus as you may remember from the homework, it's the dimension of your code minus the degree of your generator polynomial, which is 16. And the minimal distance, which I believe is actually the correct, actually the actual distance, as it turns out, is at least 7. And it turns out I think it is actually equal to 7. We can check me on Wikipedia, I guess. And so this is so script C is a length 31, dimension 16, minimum distance 7 code, and it corrects 3 errors per word, per code word, and there's 16 information bits per 31 transmitted. And so this, this is a pretty good ratio, right? This is sort of like pretty close to not much, not just a little bit. In fact, a little bit less than two, a little bit less than 2 information bits, transmitted bits for every bit of actual information that gets transmitted. And actually, I mean, and the actual the precise, like how long you want your code word to be, and how many errors you want to be able to correct for within that code word, that all kind of depends on your application. And so I think you can, people, I've seen engineers, I don't want to make fun of it. I'm not making fun of engineers. I'm saying that I've seen folks write papers about like how they have this particular model for how often errors occur, and that will depend on the physical situation of how you're actually going to use your code. Is it inside a chip? So I have a laptop right here, so it's somewhere inside. So it's so one of the things you see in real life is you see error correcting memory, because occasionally like some cosmic ray comes from above and zaps your memory chip and will randomly flip a 0 to a 1. This is the sort of thing you have to worry about these days. If you have like gigabytes or terabytes or whatever of memory, you have to worry about, like, every once in a while some bit will randomly get fried and your plane falls out of the sky. So it is a good idea to have this error. So if you look in sort of modern memory, there is error correcting memory, and sometimes there are sometimes they're more complicated schemes like the Hamming code, or sometimes they're less complicated schemes, just repetition. I think if you just sort of have 3 copies of every chip, that's simpler. So if you valued speed, that might explain. Anyway, but there are long papers about, like, given a particular model of errors of errors in a given situation, which code is better. And so it's not always sort of the best code. It could be just the repetition code. Anyway, but yeah, so this is real life, and here's how to make new good codes. So are there any questions? Whew. Thus endeth coding theory. Yes, I now see Johnny's theorem. Johnny's question again, why do we stop? Which seems to be relevant again. We stop because, well, we could go on forever, but I want to talk about, I think it'd be more educational for y'all to talk about something else. But for now, are there any questions about codes or anything else involved with this? Or are we ready to move on? So questions or move on? All right. I think, and of course, those of you watching on YouTube will say, "Oh, come on, move on. I can't help. I can't change what you already did, man." So I'll move on. All right. So what happened to the title here? So let me actually get to. So I need to talk about. So let me just say briefly what we're going to do in a few minutes. But I need to sort of either review or tell you about some stuff about complex numbers first. So what we're going to do in the last 4 classes, in the last 2 weeks of class, is we're going to talk about signal processing, which is like something completely different. And this is, so as we'll see, this is really a case of the and now for something completely different. We're going to do some signal processing in the last 2 weeks. But to do that, I need to talk about mathematically. I need to talk about complex numbers. That's sort of the language, the mathematical language of signal processing. The process by well, I don't know. So probably, I know there's some definite music people, and this people who really like are interested in music and maybe even music production. I'm going to guess. The language of so my favorite example of signal processing is always like when you produce a song, when you sort of control like the levels of the bass and the treble and stuff like that, or if you want to put in more bass or put in more mid range or put in more treble. That's an example, where you sort of break a sound down to its component frequencies and then put them back together in some way, and then maybe mess with them and then put them back together in some way. That is signal processing. And one prominent application of the math we're about to talk about, the math I think we'll sort of talk about, but maybe we might not get to the part where you guys actually have to do it on the homework, is music production. So for those of you who like music, which I think is a number of people here, that's a good thing to think about. Anyway, so first I want to talk about complex numbers. So let me remind you that a complex number a plus bi can be drawn as a pair of coordinates in the plane. And so customarily, this is the real axis, and the y-axis is called the imaginary axis. And so, for example, if we have this point over here, oops, that's right, it's hard to draw circles here. If we have this point over here, which I'm going to say is something like maybe, it's not really drawn to scale, but maybe this is like the point 5 plus 2i over here. I should move that over. Oops, and it's not 5. It's not 5. Oh my gosh, that was doofy. All right, I don't mean by 5. I mean minus 2 plus 5i, because it's minus 2 in the x direction and plus 5 in the y direction. So if we do that, then that's represented by drawing that as the point minus 2 comma 5 in the plane. So I hope everybody has encountered this. If not, you're encountering it now. I hope that sounds vaguely familiar. How to draw numbers in the complex plane like that. Can everybody say yes, or ask questions if that's not familiar? Okay, so here's a fact, which you can just think as a definition, or just sort of say like, well, this is true because I told you so. You can define. It is possible to define a complex valued function e to the I theta, and we're usually here theta is a real number. So if we're gonna do that, usually we do this so that theta is a real number, representing an angle, because that's why we're using the symbol theta. And so that function satisfies the usual properties of an exponential function, such that, but it has the following remarkable property. If you draw the unit circle in the complex plane, so again, this is the real axis, and this is the imaginary axis up here. And so this point over here is the real number 1, and this point over here is the complex number I. Anyway, so if you do that, then e to the I theta is the point on the unit circle. So if the angle here is theta, swept out in the usual way that you might remember from pre-calculus, then oops, I didn't want to do that. Then this point over here is going to be e to the I theta. So it is a fact that if we can define the complex exponential e to the I theta in a way such that what is the value? Where does e to the I theta show up in the complex plane? Well, you sweep out the angle theta, and then the corresponding point on the unit circle is equal to e to the I theta. And, oh yeah, and I guess this is often I want to discourage this because using sines and cosines is actually, it turns out to be counterproductive. Oh yeah, remember you have to use theta in radians. but you may, it's e to the I theta is cosine theta plus I sine theta is another way of saying what I just said. But I want to say you should avoid using, as we'll see in a minute. Once you get I want you to get used to using e to the I theta, because once you get used to once you get used to the idea, the computations are actually much easier if you use e to the I theta than if you try to use sines and cosines. They just get super ugly. Anyway, so and that's why I'm introducing this notation, because I actually want to make the computations that we have to do nicer and maybe even a little easier, and instead of them making sort of yucky and lengthy. But yes, it is true that you may have heard this formula, e to the I theta is equal to cosine theta plus I sine theta, which we can sort of take as a definition. Anyway, so the point, I guess the important part of this is that when you make that definition, then e to the I alpha times e to the I beta is equal to e to the I alpha plus beta. This is, if these were sort of regular exponents and the regular exponential function, you would expect this to happen. And it also works for complex exponents in the complex exponential function, which means that when you multiply points on the unit circle, it's the same as adding their angles. And I guess it's worth, so note, this is equivalent to the sum formulas from trigonometry. So I hope everybody remembers I'm sure it may well be that you don't remember the sum formulas themselves. I think I might actually have to use this. I actually remember this formula here, the e to the I theta formula, and then I generally sort of sometimes will work backwards to figure out the sum formulas. But if you ever wondered where the sum formulas come from, they come from this. They come from the fact that e to the I alpha times e to the I beta is equal to e to the I alpha plus beta. And if you sort of plug that into the this formula over here, the cosine sine formula, that actually yields the sum formulas. Anyway. All right, so yeah, I always kind of feel like, oh, people should just teach complex exponentials, but okay, I agree, that's maybe a little more thorny. It's a little more abstract, but then the formulas come out so much nicer. All right, so that's the second thing that we're going to need from complex numbers is complex exponentials. So, any questions about that? Complex exponentials are okay? Okay, so because the thing is, what we actually need here is we actually need the primitive nth root of unity. So I should draw a picture of that, huh? So the thing that we're going to call the natural primitive nth root of unity, omega sub n. So that's going to be, let me draw that on the unit circle. So that's let me draw n equals 5. So this is going to be the point e to the 2. Remember 2 pi. 2 pi is all the way around, and so 2 pi over 5 is 1/5 the way around. So this is I guess that won't quite fit in there. So this is the angle theta equals 2 pi over 5, 1/5 of the rotation. Oh yeah, all the angles have to be in radians, by the way. Make it a little bit better here. So 2 pi over 5. All right, so this point over here is what I'm calling omega sub 5. So when n is so usually what we'll be doing when we look at signal processing over the next 2 weeks is that we'll be fixing n, and so we'll be saying let's always look at n equals 16 or something like that, and I won't want to sort of write in 16 all the time when we get 16. So instead of so if we know what capital N is, then instead of writing omega sub capital N, I'm going to write just omega. And so here's the most important fact about omega sub n. It's that the powers of omega are exactly the solutions to the zeros of the polynomial z to the n minus 1, or I guess I should say the complex roots or zeros of the polynomial x to the n minus 1. There's that polynomial again, though. I said we're doing something completely different, and yet there it is again. Z to the n minus 1. This is somehow a useful thing. Are exactly the powers of omega. So here's sort of why this is. Well, I guess this is even a proof. If we take omega to the k, some power of omega, and we raise that to the nth power, minus 1, then we get, that's the same thing as having omega to the n times raised to the kth power minus 1. And remember, if we look over here, we see that if we have omega sub capital N raised to the nth power, that's by using that, because multiplication, if you multiply two complex exponentials, you add their exponents. So when you exponentiate a complex exponential, you multiply its exponent. So this is e to the 2 pi I over n raised to the nth power, which is equal to e to the 2 pi I, which is equal to 1. Right? That's sort of one of the key features of omega sub n. And so what we get over here is omega to the omega sub. I guess I better write in the capital N here. Omega sub n raised to the capital N to the capital to the k. So that's 1 to the k minus 1, which is 0. And so indeed, each of these powers is a root of the polynomial z to the n minus 1, and a polynomial can only have n roots, and so that's all of them. Oh gosh, I guess that was actually proof. I didn't mean to prove that, but there it just happened. So that's actually sort of the most important feature of omega sub capital N. And so to recap, algebraically, so let n be positive integer, and let omega be an abbreviation for omega sub n, capital N, which is e to the 2 pi I over capital N. In that case, the solutions to z to the n equals 1 are precisely the powers of omega, omega to the 0, omega to the 1, all the way up through omega to the n minus 1, capital N minus 1. And we have, furthermore, if you add all those things together, then you get 0. So that is not at all obvious, but I'm going to ask you to derive that fact on problem set 10. But let me actually, if you want to sort of know why it's true, here's why. If I draw n equals 5, so here is omega. And this is like I will. So you should always use radians because degrees are the units of Satan. But okay, I'll succumb and do this one. So this is a 72-degree angle because one fifth of the way around the circle. Yeah, because as you know, calculus totally breaks down if you use degrees, but it works great if you use radians. Anyway, all right, but I'll try to be a little bit comprehensible and use, because I know we all think in degrees anyway. It is true. And so omega squared is over here, and omega cubed is over here, and then omega to the 4th is over here somewhere, roughly. Oh yeah, and here's 1, which is omega to the 0. And if you look at this, what happens here is that this makes a little, let me see, make a very faint pentagon. This makes a sort of very faint regular pentagon around. It's supposed to be a regular pentagon, even though it came out quite irregularly. So those powers of omega make or should be, if I drew this correctly, would make a regular pentagon around the origin. And the point is this. point is the sum of the powers of omega is going to be equal to the average. So it's going to be equal to n times the average of the powers of omega. But if you average out, but what is the average position? This is the same thing as going to be n times the center of gravity. This is not really a proof, but here's sort of why this is true. Here's a good way to think about it anyway. The center of gravity of the regular n-gon is equal to n times, well, what's the center of gravity of the regular n-gon whose center is at the origin? Well, it's 0. It's the complex number 0, which is 0. So this is the way I like to think of it. This is like my picture in my head and perhaps in my heart of what's going on with the powers of omega. But there's an algebraic version on problem set 10, which is due on Monday, right? But in the long run, the important thing is to remember that fact is true, which we'll need in a minute. So, any questions about that so far? Actually, let me take a quick survey. I'm gonna box this thing in orange. So, oops, that's not what I want to do. Oops. So, how many of you have seen this formula before? I'm really curious. So just say in the chat, have you seen this formula? There's no shame if you haven't seen it before. I would actually, it's my experience that mostly people, has anyone, so have you seen this formula? Just say in the chat, have you seen this formula before, yes or no? Yeah, and I'm going to assume that everybody. Yeah, that's yes, Johnny. That's right. It's also, you can also think of it as, you could also prove this as a geometric series. It's a formula for the geometric series, and that's actually what's going to happen in the homework. Yes, that's right. Exactly right. It's a geometric series in omega, and that's exactly where the proof comes from, the homework. Yeah. So, but yeah. So I think this is not something. For some reason, this is something that kind of falls through the cracks of our various courses. It's actually sort of something I would sort of expect you not to have seen, just because there's no particular place in our curriculum that would do it. But it's such a wonderful formula that, if you don't get anything else out of today, you learn this formula. It's just such an awesome formula. Okay, anyway, so you haven't seen it before. Now you've seen it. It's this orange formula here. This is like one of the secrets of the universe. It's one of the secrets of the universe, man. I mean, it really is. Okay, so now let's talk about signal processing. Yes, and now for something completely different. Okay, so fix a positive integer capital N. So we define this is not the way, if you took electrical engineering course, probably, and if most electrical engineers saw this, they would have one or two reactions. Most electrical engineers would say like, what is this? What are you talking about? I know what a signal is. This is not a signal. Or a sort of mathematically sophisticated electrical engineer might say something like, oh, come on, you're just taking like a regular definition and dressing it up with nonsense, which is true, but it's nonsense that's convenient. That's a sort of abstraction that's convenient to us, at least. Okay, so apologies to electrical engineers. A signal for us is going to be a function from z mod n. So remember the domain. So this means the domain of this function will at least look like 0, 1, 2, all the way up to n minus 1, capital N minus 1. Oops, let me move that around. So that's z mod n to the complex numbers. So it's an input. The input is some integer mod n, mod capital N, and the output is a complex number. Yeah, complex valued functions with domain in z mod n. So because a signal is, so how would you write down a formula for this thing? Well, something you might not be used to is usually if you're in like calculus or whatever, if you write down a formula for a function, there should be some algebraic expression in the inputs. But here, because there are only capital N values, the most straightforward way to write down a complex valued function is just write down what the N values are. I mean, there are only finitely many outputs, so you just write them all down. And so we will often think of a signal as this, exactly this vector f of n through f of 0 through f sub f of n minus 1. And sort of, I mean, you don't need to know this mathematically in order to sort of go like do the homework and sort of do the problems. But the idea sort of, I guess the idea, let me actually, let me just draw a little cartoon. Yeah, so let me draw just a quick cartoon of what the idea is. So here is the idea, the picture behind thinking of a signal whose domain is z mod n. As a periodic signal, as a signal of period n. So the idea, and the idea is something like this. So in practice, I mean, so in practice, oops, 0, 1, 2, up to n minus 1, and then you have n here. So in practice, if you have a signal of period n, it would look something. Well, what you do is if you take, so here's sort of you can think of this as being like a sound wave. In practice, you don't actually often in sort of in today's digital world, or maybe yesterday's digital world, but still, in practice, you don't sort of measure what's happening at every single instant. What you do is you take samples, right? You take a sort of level reading at every given time, and then if you so what you're really dealing with is a discrete function. And so and then what happens is that if your period is n, then what happens is that you whatever happens at time 0 through n minus 1, if you're taking a sample once every unit of time, then it's just going to repeat. And that's sort of the repetition. The repetition every n time units is modeled by the fact that n equals 0 in the ring Z mod capital N. So yeah, so this is why we think of a signal whose domain is Z mod n as being a sort of periodic signal with period n. Anyway, so that's sort of why we do this. Right, so that's why we think of so see below here. That's why we think of a signal whose domain is Z mod n as being something as a sort of regular signal. You might see a squiggly thing on an oscilloscope or something with period capital N. So here's one prominent example about this. If we fix some k between 0 and n minus 1, one particular example of a signal, a very important example of signal, is if omega is omega sub capital N equals e to 2 pi over capital N. Then this is sort of like, then if you look at the powers of omega to the k, so this is omega to the k to the 0, and this is omega to the k to the 1, and so on all the way down to this is omega to the k to the n minus 1. That is one example, prominent example of a signal. And this is sort of like, this is kind of like something like it's sort of, it's not like that. It's exactly this formula actually this particular signal actually does have a sort of nice analytical looking formula. This is basically well, it's going to be cosine. I know I said not to use cosines, but but it may actually sort of work, be helpful here. E to the 2 pi k over kt over capital N plus I sine. It's not obvious that what I'm writing here. E to the 2 pi kt over capital N. 2 pi k t, where t is some element in Z mod n. So so the point is that basically, if you've ever seen something about signals before, so there's a sort of field of signal. We can think of this field of signal processing, or the field of mathematics called Fourier analysis, where we express sort of all signals as linear combination of these signals. And so our motivating problem is, as we'll see, how can we efficiently? So we can think of these as sort of being fundamental sine waves or cosine waves, sort of pure tones. Yeah. So maybe better. I shouldn't have said sine waves. I should say pure tones. Pure tones. Say, oops. I didn't want to do that. Yeah. So our motivating problem is, given a signal, how can we express such a signal as a linear combination of pure tone signals like exactly those over here? Okay. So let's talk about how to do that. So the formula for doing that is called the discrete Fourier transform. And so here's the definition of that. So again, we're fixing in sort of a period capital N, and we let omega be e to the 2 pi I over capital N, be our usual thing. That's our omega will be our abbreviation for omega sub n. This is omega sub capital N. And let F be a signal of period capital N. So we define the DFT, which is DFT is an abbreviation for discrete Fourier transform, of F to be F hat, to be the function F hat whose domain is Z mod N, and whose codomain, whose outputs are complex numbers, be given by this. The F hat of K is equal to the sum, the average, the sum 1 over n times the sum from little n goes from 0 to capital N minus 1 of F of n times omega to the minus nk. It turns out, because roughly speaking, the way we can interpret this is that yeah, what's going on here? So this is if this as a function of k, what this is roughly well, what's going on here is what I will I'll be able to explain later. So this is what turns out is that these f hat of k's are the coefficients of the pure tones making up F, and I will actually explain that in about 5 minutes. But anyway, so because of that, because these f hat of k's actually correspond to the pure tones that make up our original signal F, we think of f hat of k as the spectrum of F, because roughly speaking, f hat of k measures the strength of the part of F that has frequency k. Yeah, frequency, not wavelength. That's right. So it is actually a homework problem to actually just sit here and write that out. So if you write out the definition of f hat of k for k equals 0, 1, and 2, and 3, then f hat of 0 is the average is just the average of the values of f of 0 through f of n minus 1. F hat of 1 is the average sort of weighted by omega to the minus 1, omega to the minus 2, and so on. Blah 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 blah. So if that's what happens when you write out that formula, and see the homework. Again, this is actually your other homework problem. So at least we touched on all the homework problems before it was ostensibly due. I know everybody is behind, including me, but see problem set 10 for where you're going to get your chance to do this in particular examples. Okay, so now so now I want so that's how the DFT goes. And so what I want to show is that what we want is that we will show that momentarily. I think that's what where we will end up for the day. That so we're going to show that that our original signal f is actually equal to, oh, sorry, not f of x, but f of n. So we'll show that if when we define f hat of k in this manner up here by this strange little formula, then that allows us to reconstruct. So and now this is a pure tone signal. And so what this tells us is that if we combine the pure tones, omega, this is like omega to the k parens to the n. So if let's call that e sub k of n. So if you combine these pure tones with exactly the coefficients coming from the f hat of k's, you get our original signal back. Oh yes, there we go. So yeah, there you go. I knew we were going to prove that. There it is, right there. So the inversion theorem for the discrete Fourier transform shows that if you start with a signal f and you take its DFT, and you get this other thing f hat, which is technically, according to our definitions, a signal, but it's helpful. It's helpful more to think of it as a spectrum. And then if you do the inverse, if you then do the inverse discrete Fourier transform, you get f back. And so so this is called the inversion theorem because it tells you that you can given the Fourier transform, you can do essentially the same thing. Yeah. So let me observe that this formula over here is essentially the same thing as the DFT, except there's a sign change. So anything you can use to compute the DFT, you could use to compute the inverse DFT. And so this allows so you can use the inverse DFT to recover our original signal from its Fourier transform. Right. And so we're going to prove this. I guess right. Oh my gosh, I can actually sort of get to the end here, but okay. So from problem set 10, this is a problem on problem set 10. So again, we're going to fix. So I want to prove this theorem. I want to prove that when we So we want to show. So the point is, we want this to be equal to our original signal, f of we'll use f of x instead of f of n. So in order to do that, we're going to use what we call the orthogonality lemma. And all right, so I should say what orthogonal means. So orthogonal means is is the fancy mathematical way, the fancy pants way of saying things that are right angles. And so what this tells us essentially, so here's this formula, which I'm just going to use. And what was this? The meaning of that formula is that this tells us that the pure tones are at right angles of each other. In signal space. Oh, I got all cosmic on you, right? In signal space, man, the pure tones are orthogonal. But yeah, that's actually, I mean, that's, you know, if you do this in some sort of fancier way, that's actually the way you start to think about it. You want to think about, you think about the space of all possible signals, man. But you think about the space of all possible signals, and in the space of all possible signals, the pure tones make up like a sort of unit basis, a unit, sort of unit coordinate axes for the space of all possible tones. Yeah, I'm somebody's lol. No, but you know, it's like the most cosmic sounding thing, but this is actually the right way to think about it. This is the way the universe is set up. It's lovely stuff. Okay, so let me, in the remaining 2 minutes, let me sort of actually go through this proof. So right, so we would like the results of applying the inversion formula to the Fourier transform to give us back our original signal. So let's go through and do this. And I think I'm going to need another page here, and this is where we will stop. Okay, so let me make a little space for myself. Right. So by definition, if I take this term here and I expand it, that is the definition of the invert. That's the DFT. So if I just write out if I just take the formula for f hat of k, then you get this. Now, if I copying over, if I now so you know, so much of math basically, it's actually one of my little theories about life, that basically every field of mathematics comes down to switching the summation signs. Basically, that's all there is in math. There's like switching the summation sign. Well, you know, every field of mathematics comes down to switching the summation signs and one other technique. And I guess in algebra, that technique is having like lots of definitions. But okay, so anyways, so we're going to switch the summation signs here, which we know something good is about to happen if you're switching the summation signs. So instead of summing over n on the inside and summing over k on the outside, I'm going to sum over k on the inside and n on the outside, which is okay because this is a finite sum. And so if I now combine the omega terms, I get omega to the so the product of this thing becomes omega to the kx minus nk, which if I factor out the k becomes omega to the k times x minus n. All right. So there's that. Yeah. So sort of, yeah. So again, the point is here that these two omega terms put together have a product of omega to the k, like multiplying the multiplying these the exponentials is the same as adding the exponents. So we get that over here. And now the point is, by the orthogonality. Oops, that's not what I wanted. I want to do this. I want to do this. Hang on. By orthogonality, we see that that this is over here is n is zero if x is not equal to n, and is equal but equals capital N if x is not equal to little n, and is equal to actually, let me put it this way. So by the orthogonality, I know I have -1 minute left, but I'm going to get it done. By orthogonality, if little x equals little n, this is equal to capital N, this term. Otherwise, equal to 0. So if you go back up and look at what as we see over here in this orthogonality relationship, then this thing that I'm about to circle in green. Oh no! This thing that I'm about to circle in green. There we go. Is equal to capital N when little x is equal to n, and otherwise is equal to 0. And so this comes out to, okay, negative 2 minutes left, 1 over capital N of the sum as little n goes from 0 to capital N minus 1 of, well, the only time this happens is when x is equal to little n. And so so there's only one term left from the green sum, which is a single capital N. Oops. A single capital N. And this is oh shoot. And I seem to have made a, oh yeah, right. So sorry, this is this n is on the outside. So this only happens. I made a mistake here. My bad. And so so this outside sum goes away. My bad. So the outside sum only counts when x is equal to n, and so we get f of x times capital N. Right. So so this only counts when x is equal to n. And so so we get a single term here, and this is equal to f of x, and so we get f of x. All right, so there's a slightly ignominious ending to all this, and I have negative 3 minutes left. So I apologize for going over time. I'm sure some of you have fled. Sorry for going over time. So thank you very much, and you can go look at the last bit of this on YouTube. So thanks very much, and see y'all on Friday. I hope for the problem session, and see you on Monday. See you Monday for sure. Okay, let me stop recording and.